This example is, let's name it the paper company. So suppose we have that black paper, and let's assume the length of these big paper is 1 meter, and we want to create we want to cut these big paper into smaller pieces. And you can see these are the requirements. So piece X has a width of 5, and piece Y has a width of 7, and piece Z has width of 9, and they have the same length of the black one. Okay, so the question is, how should I cut the paper in order to minimize the number of big papers I have to use? For example, let me give you an example. If I want to cut this big paper into and create some X piece, it means that each paper can give me 4 pieces of piece X, yeah, and also it can give me 2 pieces of these red ones, or 2 of these yellow ones. Okay, and there are some parts are lost, yeah. So how should I do that in a way that the number of big papers that I'm using is minimized? Okay, so definitely I have to choose the binary variables. Okay, so I want to know for each piece of paper, let's call it I, how many X I can extract, how many Y I can extract, how many Z I can extract. For example, 1X, 1Y, which will be 12. I can't do any more Z because the width of the paper is not big enough. Okay, or what else I could do? I could say 5 and 2 pieces of red. It will be 19. Yeah, it's less than 20. Okay, so 5X plus 7Y plus 9ZI should be less than UI. Yeah, so it's better to write it down. It's okay. This example is called the paper company. Suppose a paper company should cut its raw papers, which you can see them as the black big papers, into the color ones, and the size of each color paper is known, and also the black one as well. And I want to know how should we optimally cut these big black papers into the color ones. Okay, so let me give you an example. If I only need the X kind of size, it means that each black paper can give me 4 of these green ones, or 2 of these red ones, or 1 green and 2 red, yeah, or 2 yellow ones. Okay, so the width of the paper should be always taken into account. So we want to minimize the number of big papers I'm going to cut, and for each given paper, how many X and Y and Z I can extract. So 5X plus 7Y plus 9Z less than 20 UI, and NX, NY, and NZ are telling me the required number of each piece. Okay, as you can guess, I have to define them as binary variables. Okay, so let me show you the code. So here I import the required packages I defined as a concrete model, and also you can see here that U is a binary variable, and X and Y and Z are, let's say, integer non-negative integer variables. Okay, So first rule, 5x plus 7y plus 9z less than equal to 20 ui. And the next rule is specifying how many of x is required. So let's assume that nx is 10, ny is 12, and nz is 5. You could define them as some parameters. It would be much better and professional, but that's fine. And the objective function is summation of I multiplied by ui. I could omit the I multiplication here, but I will show you why I put it here. And also the solver I'm going to use is GLPK because it's linear programming, and the results are found here and everything is calculated here. So for example, by this answer I know that there are 10 big papers are needed. The first one is giving me 1x and 2y, the second one the same, the third one is only using 3 for x, and so on and so on. Okay, let me run the code from the beginning and show you the results again. Okay, this part is executed. Now the program is running the optimization part. But one question is here that how many big papers I should consider for my optimization, because initially before solving the problem I don't know how many papers are needed. So I define a big number at the beginning. Okay, so how can I determine that? By looking at the number of required x, y, and z, I can say this is the maximum number of big papers that might be needed. Okay, so so at the end I know that 10 papers are needed. So let me check something else for you before I finish this example. If I remove this multiplication, what will happen? Guess what? So I run it from the beginning. So I'm waiting for the solver to finish the job. Okay, I just slightly modified the objective function. And I'm waiting for the solver to finish. Okay, so have a look at the results. This is exactly what I wanted to show you. So you can see that it's 1, 3, 5, 7, 8, 9, 10, 13, 14, and 15. Okay, so the objective function is telling me there are 10 pages are needed, exactly the same as before, but it doesn't matter for the solver that which page is being chosen, so the page with higher rank or lower rank. I mean, they are not sequential. You can see here 1, 3, 5, 7, 15, you see. So but if you multiply it by I, it will give you a more kind of clean solution. Okay, thank you very much.